In the name of God. Today we are going to talk about ant colony optimization. The ant colony optimization is a meta-heuristic algorithm in swarm intelligence category. In meta-heuristic techniques or algorithms, we have different category of algorithms. The one category is swarm intelligence. The algorithm like particle swarm optimization we will study in the future. Ant colony optimization, fish swarm optimization, bat swarm optimization, and there is lots of different algorithms in this category. Another category is evolutionary algorithms. The evolutionary algorithms like genetic algorithm, evolutionary strategy, evolutionary programming, and other methods. Also, some category of meta-heuristic algorithms are probabilistic-based methods like simulated annulings. Could be hybrid methods like hybrid meta-heuristic, memetic algorithms, and also it could be neighborhood search heuristics like taboo search and variable neighborhood search algorithms. In the previous lectures, we study taboo search algorithm and simulated annealing and genetic algorithms. Then you have idea and information about this type of algorithms. And now we are going to talk about ant colony optimization, one of the main algorithms in swarm intelligence category. Swarm means population. Swarm intelligence means intelligence by collection of items, animals, cells, and everything. A collection of different items, collaborate, communicate, work with each other to do some tasks. The scientists study the behavior of animals or some things in the nature and tried to study and understand and based on them presented the algorithm that we can use it in solving optimization problem. The main idea of swarm intelligence is you considered, suppose you and a group of your friends are on treasure finding mission. Each one of in the group has the metal detectors, can communicate and signal the current position to the end nearest neighbor. Because in wide area you didn't know the position, the location of treasure or metal or gold, and then you use the gold detector to find the gold or the treasure location. Because nobody know the exact location of that, then everybody travel and spread around the environment and check its neighbor, the environment. Each person therefore knows whether one of his neighbor is near to the treasure than him. If this case, you can move closer to that neighbors. When how you know your friend have the close the treasure? By receiving the signals. When the detector, the metal detector detects a gold or iron or everything, send the signals. By receiving the signals, you can learn, you can know that there is a treasure in that location, and then in this case, you can move closer to that neighbor. In doing so your chances are improved to find the treasure. Also, the treasure may be found more quickly than if you were on your own. Because you receive some signals and then you change your direction and get closer to your friends because he have some signals. By this way, you and your friend collaboration could help to find a treasure very quickly and efficiently. In the ant colony optimization, when at the first the ant goes up from the nest, then spread in many directions, in this side, in this side, in this side, in this side, in every different location, everyone. So every ant travel by different ways. Some of them didn't find any source of the food, like this pat. After 2 hours, more ants are available to forage because they cannot find any food. So nobody want to travel in this path. But there is a source of the food here. Some of the ants find the source of the food and they return to their home. They can return in this way or in this way to the nest. When they return to the nest, they spread a pheromone, a liquid. They spread the pheromone in the path to understand the path from nest to the food and then come back to bring the food to the nest. For example, in this way, because it is the shortest path, in 20 minutes, 15 trips completed in 20 minutes. But in this path, because there is a long and there is a lot of long from the nest, then in 30 minutes, only 6 trips was completed. Therefore, you see, this is thin and this is thick. So this path is strong path for traveling. How the animals, how the ants now this path is shortest. Therefore, the main idea behind this, in a series of experiments on a colony of ants with the choice between two unequal length paths leading to the source of the food, biologists have observed that ants tended to use the shortest route. A model explaining this behavior is as follows. An ant runs more or less at random around the colony. So at the beginning, every ant move or travel in the random way. If it discovers a food source, it returns or more or less directly to the nest, leaving in the past a trail of pheromone. The pheromone is the liquid. Then when the NAMLA, when the ant spread the pheromone on the path, then other ants can smell and then follow that path. These pheromones are attractive nearby ants, therefore nearby ants will be inclined to follow more or less directly the track. So because one ant finds the source of the food and spread the pheromone on the path, other ants now there is source of the food and then come to that direction and they travel from the nest to the food source. Returning to the colony, when they go from the colony and the source of the food, these ants will stretch the routes. How? If two routes are possible to reach to the same food source, the shortest one will be in the same time traveled by more ants than the longer routes will, because it takes more times for traveling. This shortest route will be increasingly enhanced and the long routes will eventually disappear. Pheromones are volatile. Therefore, in 1992, a person named Darigo proposed a heuristic optimization method inspired by biology systems. Based on the behavior on ants in the nature. Therefore, population-based algorithms for solving different combinatorial optimization problem was proposed. The problem like traveling salesman problem, vehicle routing, sequential ordering, graph coloring, routing in the communication network, it's very, very complicated problems. And it is not possible to solve these problems in reasonable times. Therefore, we need an algorithm like ant colony for solving this type of problems in the short period of the time. Ant behavior is a kind of stochastic distributed optimization behavior. So it is stochastic, it's not deterministic. It's something like random size, something like probabilistic. So it is the kind of stochastic distributed optimization behavior. So every ant has to have its own path, its own direction. Then each ant using a Stigmergy, it's sampling, it's signing the paths traveling. A term coined by French biologist Pierre-Paul Garcia is interaction between the environment. So they spread pheromone on the path, then sign the path for other ants to follow that path. Two individuals interact indirectly when one of them modifies the environment, and the other responds to the new environment at the later time. By this way, two ants interact indirectly, so they have no direct interaction between ants. They only communicate with each other indirectly by spreading the pheromone on the edge. And by this way, the other ants respond to the new environment at a later time. Pheromone trails. Species lay pheromone trails traveling from nest to nest or the possible in both directions. The pheromone have the attributes that it evaporates. Evaporates means tabkhir. Yeah, evaporates and then disappear after some period of the time. When many ants travel one roads, then many ants spread the pheromone on that path direction. Then pheromones accumulates with multiple ants using a path. When the many ants travel in one direction, the one path, then the amount of pheromone in that path increases and causes the strength of the path. Like this one, you see? Because this is the shortest path, many ants travel from the nest to the source of the food. Then, because many ants travel in this direction, all of them spread the pheromone in this direction, in this path. Then they causes the path to be strange and strange and strange and strange. Finally, at the end, all the ants travel from this path, and then other path will be disappear from after some period of the times. Like TSP problem. TSP problem is traveling salesman problem. You see, there is many cities. One city, this is the cities. We want to find the shortest path This is the cities, different cities spread on the map, like our country, your country, and other country, every country in the world. You see, there is different direction, different routes, different ways between the cities. At the beginning, we want in TSP problem, we want to find the shortest path for traveling by the salesman. So traveling salesman problem is the problem that al-bail mutajawwil travel and visit all the cities one time and then return to the original city. We want to help TSP, traveling salesman, to find the shortest path for traveling all the cities. Therefore, you see at the beginning, all the ants travel in many different directions. But after some period of the time, you see some of the edges will disappear. And some of them get stronger and stronger. So the algorithm repeats from this direction and then continue. And finally, as you see, some of the edges was stronger and some of them will disappear, and there is no edge here, for example, here and here. So by this algorithm, by combination and the collaboration between different ants, we want to help TSP, traveling salesman, to find the shortest path. How they do this? So the ant colony optimization for solving the TSP problem, at the beginning, it initialized the pheromone amount of each road with the positive small random number. As you see here, let me discard this changes. At the beginning, all the edges, as you see, have the small number of pheromones, initializing the pheromone amount of each road to a positive small random value. Then a simple transition rule from choosing the next city to visit is, when the ant is in this city, for example, this one. Yeah, this city. Yeah. The ant is this city want to travel from its neighbor. Could be this one, could be this one, could be this one, could be this one, and all neighborhood cities. So the ant want to travel from the city I to city J. So this is one travel from the city A to city J. K is the count, is the number of ants. T is the time. So at the time of T, the ant want to travel from city A to city J. Which ant? We have many ants because this is the population-based. In the population-based algorithm, we have many ants, and each ants help to each other for solving the problem. So we want to travel. There is parameters tau. Tau means amount of pheromone between city I and city J at time of T. We want to find the shortest path. Therefore, we select, when we are city A and we want to travel for the next city, we select the city with more ants. We select the city with more ants. Therefore, the phi ij k at time of t is equal to tau ij at time of t power of alpha. There is no problem how alpha could be different numbers. So selecting the next city, it's based on the tau. At the beginning, because the amount of the tau is all the routes is the same, so no difference. The ant select one of them. But after some period of the time, as you see here, the ants, all the tau on all the edge is different. So as you see, when we come to this city, the ant only select this one, because this route is stronger than all the routes. Because the amount of pheromone spread on this edge, it's more than other edges and help to increase the amount of pheromone and stretch that paths. So in ant colony optimization, when one ant number of k, want to travel from city A to city J, try to select an edge with the highest amount of pheromone. If you want to help TSP problem algorithms, especially in the initial steps, we add another heuristics. We add another terms. The transition rule above can be improved by including local information on the desirability of the choosing city J when currently in city I. So when we want to select next visit, we add another part, eta. Eta ij power of beta. What is the eta? It's a heuristic, where the alpha and beta is adjustable parameters that control the weight of pheromone intensity and eta ij. Eta ij is the diverse of distance. When the distance is the high, then the number of eta is low because it's the inverse of distance. But when it's short, the number of eta is high. So help the algorithm to select the shortest path. So instead of having only one parameter in this formula, now we have two parameters, tau. Tau is the amount of pheromone in that edge between CTI and the CTJ, and eta. Eta is the CTI and the CTJ. Therefore, we use the adjustable parameters that control the weight. This is the one heuristic. We add the algorithm for traveling. This is the distance between CTIJ. It is based on the Euclidean distance. At the end of each route, Tk, the amount of pheromone between CTIJ at time of next time plus 1, it's equal to amount of pheromone in previous time, multiple 1 minus rho, plus delta tau ij at time of t. Yeah, this is clear because each city between CTI and the CTJ, we have amount of friend spread on that edge. But depend on how many ants travel from CTI and the CTJ, the delta ij is different. So the delta ij at time of t could be amount of pheromone spread between CTI and the CTJ by different k ants. We have k equal to 1 and m, this is number of ants. So we have many ants. The summation of all pheromone spread on the edge between CTA and the CTG at time of t, but different edges, we summation of all of them is the delta tau ij. So by this way, we increase the amount of tau between CTI and the CTJ. Also, there is another parameter, 1 minus rho. May you can think about it. What is the rho or 1 minus rho? For a moment, don't then continue for listening the video. So the delta ij could be the amount of pheromone spread on the edge, could be inverse of length of tours. When the one ants start from here, have a long path for traveling, so the amount of pheromone between paths is very, very low. But if the ants travel from the shortest path, therefore the amount of tau spread on the edge between CTA and the CTJ is high. So this is the amount of pheromone spread on the edge between CTI and the CTJ is L, length of the optimal routes. The parameters phi has the value of the same order of the length of the optimal tour. So L is the length of the route travels by ant k, and the m is the total number of ants. So we have many ants traveling. When the one ant travels between the city, the length of the tour, the length of the route traveled by ant k is Lk. The amount of pheromone is the inverse of the length of the tours traveled by the ant. By this way, if the length of the tour is the high, then the amount of pheromone spread is the low. If the ant traveled by the shortest path, then the amount of the pheromone spread is the high. By this way, the shortest path will be stranger than in previous step. But the long path will be the amount of pheromone in longest path will be decreased, and finally it will be disappear. The constant rho in this formula we have 1 minus rho. The constant rho is referred as the forgetting factors, which model the evaporation over time of pheromone deposits. As I told you, the pheromone is evaporated. It's tabkhir, change to the bukhar. So it's evaporated over the time. By this way, every time when we calculate the amount outside, we consider the evaporation. So the 1 minus rho, it could be 90%, for example. So the amount of pheromone at that age, it's 90% of previous pheromone plus delta. So then here could be, for example, 90%. It depends on the rho. If the rho is the 10%, so every time we calculate the amount of pheromone between CTA and CTG as time plus 1, it's amount of pheromone at previous time multiple 1 minus rho. So by this way, we simulate the evaporation and increasing the amount of shortest path. When there is traveled in the shortest paths, the delta is very, very high in comparison with the longest tour. So if you consider, when you go out in the nature, you see the ants travel one direction, you can put a stone, an obstacle in that direction. Then after some period of the time, most of them travel from the top because it's short, and some of them travel from the down. But after some period of the times, all of them travel from the top part of the obstacle, and then they select the shortest path very, very heuristically. So by this way, we update parameters evaporation plus stringency. Update amount of pheromone in the path from node I to node J. So tau ij at time plus 1 equal to 1 minus rho tau ijt plus delta tau ijt. So it is evaporation and improvement. So consider this one. At the beginning, between A and we want to travel between A and E. The distance of this side is d equal to 1, and the distance from this side is equal to 0.5, so it is shortest. At the beginning, when the ants want to travel from the E to A, or vice versa, no difference. So 30 ants start traveling, and then 15 of them traveling from this part, and also 15 of them traveling from this part, because they don't know the length of the tour and distance of different paths. But after some period of the times, as you see at tau, for example, tau t equal to 1, now 20 ants travel from this side, and only 10 of them travel from this side, because the ants work with each other, help each other, and select the best paths for traveling, and select the shortest paths for traveling. There is different type of ant colony optimization algorithm. One of them ant colony system, elitist ant system, max mean ant system. So there is different type of ant colony optimization based on the different algorithms and different situation and different problem. May you select one of them, and in most cases ant colony optimization, as you see here in the green, in the most cases the tour length traveled by the ant colony optimization is better than all other. But as you see in the finally, the min-max colony ant-colony optimization finally bring the better result than ant-colony optimization. But in the most cases, as you see from the beginning to this point, the ant-colony optimization is better than other algorithms. So it could be used for solving many different algorithms. And for example, on TSP problem, the algorithm travels and simulates the behavior of ants, and then finally find the shortest paths as you see here. Some edges will disappear as you see here. It was disappear. Some edges are okay, but this one is very, very strange one, and then unselect this path for traveling. So if you want to use ant colony optimization for solving TSP problem, at the initializing, then we randomly place ants in different nodes, different cities. We build tours. Every ants after traveling deposit the amount of friend, then update trails, then loop this problem many times until they exit. So this is the idea behind using ant colony optimization for solving TSP problem. I leave this TSP problems solving with ant colony optimization as the homework for you. You must do it and send it by email to me. Yeah, this is the all idea behind this type of algorithm. Therefore, in this lecture, we talk about ant colony optimization. You can study the concept in any text, any other videos, any in Arabic, in English, in Farsi, in any language you want. But the main thing is that understanding the concept and using the ant colony optimization for solving the optimization problem.